We're now going to start looking at a class of functions known as exponential functions. And they're different from polynomial and rational functions in that in those kinds of functions, the variable was always being raised to constant powers. We'd have something like x squared or x cubed, so forth. In exponential functions, the variable actually appears in the exponent of these expressions, whereas the base of the expressions is constant. And these functions have many applications in the world of finance, biology, other sciences. So let's just quickly recall some rules about how exponents work. If I've got something like 5 cubed, that by definition just means take 3 copies of 5 and multiply them all together. If I take a number and raise it to the 0th power, a number other than 0, and raise it to the 0th power, I always get 1. And then if I take a number like 3 and raise it to a negative integer, like -2, that's the same as 1 over 3 squared, which is 1/9. And these 3 rules allow us to raise any positive number to any number to any integer power, positive, 0, or negative. We also can raise positive numbers to fractional powers. So we could take something like 25 to the 3/2. By definition, this is either, we can write it 2 different ways. We can write it as the square root of 25 cubed, or as the cube of the square root of 25. The square here in the square root coming from the fact that 2 is in the denominator of the fraction. And so from there we get that this is 5 cubed, which actually works out to be the 125, the same as the top. So the question is, how do we handle something like 3 raised to the square root of 2? We can't use any of our previous rules for this because the square root of 2 is irrational. It cannot be expressed as a fraction. And therefore, none of the previous lines apply. In order to work this out, what we do is, first of all, note that when you're working with a calculator, which we'll do in a second, then you can usually just plug expressions like 3 raised to the square root of 2 into the calculator and get an approximation for it. But in order to understand how that approximation is arrived at, let's look at the process. Now, the square root of 2 has a decimal expression. It's not a fraction, but it does have a decimal expression. And that starts 1.4142. Now, what we want to do is we want to look at a sequence of rational numbers that are getting closer and closer to the square root of 2. One way of doing that would be the following. We could look at the numbers 1.4, 1.41, 1.414, 1.4142, etc. And what we see here is that each one of these numbers is rational because their decimal expansion stops, and they're getting closer to the square root of 2. The technical term for this situation is that this sequence of rational numbers converges to the square root of 2. Now, the fact that that helps us determine the exponential, it actually relies on some pretty powerful theory, which we don't have time to get into here. So we've got these expressions, these sequences rather, and we can use them to say, all right, well, we don't know what 3 times the square root of 2 is, but we can look at what 3 raised to the 1.4 is, what 3 raised to the 1.41 is, what 3 raised to the 1.414 is. And all of these expressions can be computed using the rules of the left side of the screen, because 1.4 is a rational number. 1.4 is the same as 14 over 10, which means that 3 to the 14 over 10 is the same as the 10th root of 3 to the 14th. And similarly, 3 to the 1.41 is 3 to the 141 over 100, and so it's the 100th root of 3 to the 141. And these continue. Now, if we were to work these things out, we'd get the following. 3 to the 1.4 is 4.655, etc. 3 to the 1.41 is 4.706, etc. 3 to the 1.414 is 4.7276, etc. 3 to the 1.4142 is 4.728, etc., etc. So what we can observe is that the numbers that we get when we raise 3 to this sequence of rational numbers that are getting closer and closer to square root of 2 are also getting closer and closer to some number. And so these numbers in blue are approaching some number, which is approximately, looks to be approximately 4.73 if we were to round it to 2 decimal places. So when we raise 3 to numbers that are getting closer and closer to square root of 2, we get approximately 4.73, which means that we should take a guess that 3 times the square root of 2 should be approximately 4.73. In fact, this process is how we define 3 raised to the square root of 2, and that's how we extend the definition of exponential expressions to ones that involve rational exponents. Now, we can also use a calculator to do this, and the calculator will use a similar sort of approximation to this. So when we go into the calculator and we write 3 raised to the square root of 2, we get 4.7288 ... which is in fact approximately equal to the 4.73 that we observed in our process. Now, this calculator is free to use. It's at Desmos.com. Desmos.com is an excellent website for lots of math tools like this. So that's the point behind how we define exponential functions for irrational numbers. And an important thing to remember is that irrational numbers in exponents behave just like any other exponents in that they follow all the same rules. So, for example, if I have something like 4 raised to the square root of 3 raised to the square root of 3, I know that when I'm working with exponents and I take an expression raised to a power and then raise that to another power, I'll get 4 to the square root of 3 times square root of 3. I multiply those two powers together. And therefore, square root of 3 times square root of 3 is just 3, and therefore we can simplify this expression down to just 64. And then if we have something like 2 to the square root of 5 times 2 to the square root of 2 to the square root of 45. This is 2 to the square root of 5 plus the square root of 45, because when we have the same base and two expressions are multiplied together, we add the exponents. This we can simplify a little bit, because the square root of 45 is the square root of 9 times the square root of 5. But the square root of 9 is 3, So we get the square root of 5 plus 3 times the square root of 5. So we get 2 raised to the 4 times the square root of 5. A lot of times we would want to simplify an expression like this further and write this as 2 to the 4th to the square root of 5, so that we can write this 2 to the 4th as just 16. So the expression that we had to begin with, 2 raised to the square root of 5 times 2 to the square root of 45, is the same as 16 raised to the square root of 5. And the point is that irrational exponents work just like rational exponents when combining expressions together or raising expressions to powers and so forth. So now that we understand exponents of any kind, any real number as an exponent, we're ready to define an exponential function. An exponential function is of the form f of x equals b to the x, where b is positive and b is not equal to 1. B is called, not capital B, b is called the base of f. So we've got exponential functions, and they're of the form some constant number raised to a variable. Now, the base has to be positive and has to not be equal to 1. The base has to be positive because if the base were negative, we could run into situations like trying to take this negative 2 raised to the 1/2, which is the same as the square root of negative 2, which is undefined. And then on the other hand, if we had 1 as our base, and we took 1 raised to any x power, then we would just get 1 back. So the point is that if b is negative, then f has a restricted domain. However, it's not as simple as just saying that that the domain of f is only positive numbers or something like this. It's actually quite weird and complicated, and we're just going to eliminate that possibility entirely. If 1 raised to the x, if 1 is the base, then 1 raised to the x is always just 1. If 0 is the base, then 0 raised to the x is always just 0, unless x equals 0. So that tells us that if b equals 1 or 0, f is a constant function. We don't want either of these. Neither of these really work well with the theory of exponential functions, so we want to only be looking at exponential functions whose domain is all real numbers and that are not constant functions. So from this, by restricting b to being a positive number other than 1, we have the following facts. The domain of an exponential function is always all real numbers, the interval from negative infinity to infinity. The range of an exponential function is all positive numbers. We'll see why this is in a moment when we go to graph them, but it's very important and relevant surprisingly often that you can only get positive numbers as the output to an exponential function. You can never get 0, and you can never get a negative number. And so as you're going through the process of working with these functions, if you ever get a negative number out of a basic exponential function like we've got here, you've made a mistake somewhere, and so you need to go back and check things. So now let's actually graph a couple of them. So the graph of exponential functions have basically 2 shapes. And the two shapes that we get depend on whether the base is greater than 1 or less than 1. So the graph of exponential functions depends on if b is greater than 1 or b is less than 1. So let's graph some functions. I want to graph I want to graph 2 to the x and 1/2 to the x so that we can compare them easily. So I'm going to make a table over here, and I'm going to handle both functions. So let's let f of x be the exponential function 2 to the x, and let's let g of x be the exponential function 1/2 to the x. So we'll make a table here, values of x, values of f, which are 2 to the x, and then values of g, which are 1/2 to the x. And we're going to look at the following numbers: -2, -1, 0, 1, and 2, and see what we get in each of these cases. Now, when x is -2, or let me start with 0 actually. 2 to the 0th is 1. 1/2 to the 0th is always 1. In fact, any positive number raised to the 0th is always going to be 1. So that's the first thing that we're going to note, is that we've got the y-intercept of any exponential function is always the same. So I'm going to label the graph this way. All right, so we've got 1 and 1 here. I'm going to, as we go through, I'm going to plot the points on the graph of f of x, but then we'll come back and plot the points on g of x. All right, so we have the point 0, 1 that's on the graph of 2 to the x. Now, if x is 1, then 2 to the x is 2 to the 1, which is just 2. So that means that the point 1, 2 is on the graph of f. And then we've got, if x is 2, then we get 2 to the 2, which is 4, which is on the graph of 2 to the x. And at this point, it looks almost like a quadratic function. It looks almost like a parabola, but that's going to change once we start moving to the lower numbers. So if we plug in -1 to 2 to the x, we get 2 to the -1, which is 1/2. So that means that we've got a point over here, -1, 1/2. And then if we plug in -2, we get 2 to the -2, which is 1 over 2 squared, which is 1/4. That's going to be even further down here, -2, 1/4. And then I do want to say, all right, well, what about 3? If we plug 3 into the function f, that'll be 2 to the 3rd, and 2 to the 3rd is 8. So we've got 3, 8 up here. All right, so there's the graph of f. Let's go ahead and connect up these points smoothly. approximately like this. Now let's do the same for 1/2 x. Now if we plug in 1, then we get 1/2 to the first is equal to 1/2. And if we plug in 2, we get 1/2 squared is equal to 1/2 times 1/2, which is 1/4. On the other hand, if we take 1/2 to the -1, remember that raising a fraction to the -1 just gives the reciprocal back. And so 1/2 to the -1 is 2. And then 1/2 to the -2, we can use up the negative in the exponent by taking the reciprocal of the fraction. And so 1/2 to the -2 is 2 to the +2, which is 4. So we have the following points, which are going to be similar to what we had for the blue, for F. So we have the point 1, 1/2. We have the point 2, 1/4. Going to the negatives, we've got the point -1, 2. And we have the point -2, 4. And furthermore, if we go back one more spot, go to -3, then we will in fact get the point -3, 8 for the function g. Now let's go ahead and graph that. So this graph illustrates basically the two shapes that we can get out of the graph of an exponential function. The exponential function is either increasing or decreasing, depending on whether the base is greater than 1 or less than 1. And there are some common things that we can see here. For instance, they both have a y-intercept at 1. And this is going to be true for every exponential function. Furthermore, they both have a horizontal asymptote. Now, unlike rational functions, where the horizontal asymptote determined the end behavior on both sides of the graph, the horizontal asymptote for the exponential function only determines the end behavior on one side of the graph. For the function f here, the horizontal asymptote determines the end behavior to the left, and the horizontal asymptote for g determines the end behavior on the right. Furthermore, we can see that the functions grow, or rather the function f grows quite quickly as we move to the right of the graph. It starts growing faster and faster, accelerating up and up and up, which is why the term exponential growth, or grows exponentially, rises exponentially, is a euphemism for rising very, very quickly. The exponential functions with a base greater than 1 are increasing, and in fact they increase quite quickly. In fact, they grow quicker than any polynomial function if you go out far enough to the right. The exponential functions grow very, very fast. And the same is sort of true on the other side when you look at the function g, or a function with a base that's less than 1. It is very, very steep, but on the left side of the graph where it's decreasing. And then when you get down to where the graph is, where the y values are small here, the exponential function gets very, very close to 0 and can get as close to 0 as you like. So these two graphs are good ones to keep in mind. I do want to give the general form of what these graphs are, which help us to identify the graphs of, or the exponential function that we're looking at. So these were the specific examples for bases of 2 and 1/2. The general graph is going to be very similar to this. So in general, the graph of f of x equals b to the x has the following properties. It has a y-intercept at the point 0, 1. It has a horizontal asymptote at y equals 0. It is increasing if b is greater than 0. It's decreasing if b is less than 0. And importantly, we can always identify two other points that lie on the graph of f other than the intercept, which help us to graph things out. So the graph always includes the points 1, b and -1, 1 over b. So that means that the graphs have two general forms that they can take. We can have the following, where we go through the point 0, 1, 1b, and then -1, 1 over b. And this is what the graph of the exponential function looks like when b is greater than 0, and then when b is greater than 1. B is always greater than 0. This applies when b is greater than 1. And then when b is less than 1, we've got, we still have the point 0, 1, and we still have the point 1, b, but now b is assumed to be less than 1, so the point 1, b is somewhere there. And if that's the case, then the point -1, 1 over b will be like this, because that'll be greater than 1. So these are what the graphs of the exponential functions b to the x look like. Also, as we saw before, we can read the domain and range of these functions here. The domains of both of them are all real numbers, and the ranges are all positive numbers, the open interval from 0 to infinity, as mentioned before. So let's see an example of how we can work with this. So we can ask, what exponential function has the following graph? And we're given a graph like this, where we can see that it goes through the point 0, 1. It goes through the point 1, 4. And looks like this. Well, there are a couple of ways of looking at this. So first of all, we check to make sure that the function has a y-intercept at 0, 1. And it does. So that's good. So we got f of x is equal to b to the x for some b. We have to determine what b it is. In this case, we can read it directly off the graph because we've got the point 1, 4. The point 1, b always has to appear on the graph of a of an exponential function. And so if you have the graph that you know is the graph of an exponential function, which passes through the point 1 comma something, then that something has to be your base. So in this case, we've got 4 to the x. So the graph of f of x equals 4 to the x looks like this. On the other hand, we could take the same question, but change up the graph slightly. So let me start over. And so what if we have this? Oops. What if we have this function? Well, this we can tell right away is not the graph of an exponential function. And we know that because an exponential function is either increasing everywhere or decreasing everywhere. This function is not doing that. This function is decreasing on the left side of the graph and increasing on the right side. It doesn't even have a horizontal asymptote. This simply is not the graph of any exponential function. All right, and then this graph, similarly, is not the graph of an exponential function. And that's because its range is not the interval from 0 to infinity. Now this one looks like it might be a shifted version of an exponential function, but we use the term exponential function specifically to refer to functions of the form simply b to the x. If you do some transformations of that, shifted up or down, left or right, reflected around the axes, that's fine. That gives you perfectly good functions, but we won't call those exponential functions anymore. We would call them transformations of exponential functions. And so this graph here is not the graph of any proper exponential function. We can use this to check things. However, let's say that we have a function that does appear to be an exponential function. And goes through the point 2 comma 49. Well, on this one, we can't say that it's not an exponential function. It certainly looks consistent with the general shape of exponential functions. It's got the right y-intercept, but we can't immediately read off the base of the exponential because we don't have the point 1 comma something in the graph, or negative 1 comma something labeled in the graph. So for this, what we can do is use some point that we do have on the graph, other than 0, 1. We've got the point 2 comma 49. So we're told that f of 2 is equal to 49. But f of 2 can also be written as b to the 2, base raised to the second power. So that means that b squared has to equal 49, which means that b has to equal plus or minus 7, but remember that the base of an exponential can never be negative. So in fact, b has to equal just 7, which implies that the function f of x with that graph is the exponential function 7 to the xth. One of the places that you may encounter exponential functions most frequently is in the context of compound interest. When you deposit money in an account that provides interests, such as a savings account, then every certain amount of time you get an interest payment. You get paid a little bit of money for leaving your money deposited in that account. Now, the next time period comes along and you earn interest on the interest that you had before. And then it happens again, and it happens again. And we'll see here that gives rise to an exponential relationship between the amount of money in your account and the time that has passed since you opened the account. So let's define some symbols here. So let's consider investing in an account. We'll let capital P be the principal, i.e. the initial amount invested. We will let A be the amount in the account after T years, where T is the number of years invested. Then we've got two other pieces of information that we need to consider. R is the annual interest rate of the account, and N is the number of times per year the interest is compounded. Now, let's start off with an example in which n is 1. So for this example, let's suppose n is 1, and that means that when we look at the account and we ask how much is in it and we go to compute how much interest we've earned, we're only going to do that once a year. So let's look at how much is in the account at various times. After 0 years, 1 year, 2 year, and 3 years. So at time t equals 0, the amount in the account is simply the principal that you invest. You take a chunk of money, you put it into the account, and that starts the clock. And the amount of money in the account is exactly as much as you started with. Now, after 1 year, the bank looks at your account and says, "Oh, thank you for investing with us. What we're going to do is we're going to take your principal and we're going to give you some extra money. We're going to pay you for investing your money in our bank, and that is going to be given by the interest rate." So you're still going to have the money that you had before, but now you're going to get an additional amount of money, which is calculated by taking the interest rate times your principal. So this is the interest that you've earned in the first year. Now I want to rewrite that by factoring the p out, so we get p times 1 plus r. Now this 1 plus r factor is going to be important for what we do later. This 1 plus r tells us how much we multiply our investment by each year. And we'll see how that is here. Now, let's look at what happens when we go to the second year. Now, I'm actually going to label these A's to help us out as we go to the second and third situation. So, if we want to know how much we have after 2 years, the same process is going to apply. Whatever we had initially is still there. We're assuming that we're not taking any money out of this account. We're just leaving it there and letting it earn its interest. So we're going to have as much money as we had there before, but we're going to add an amount of interest. So we're going to add an amount of interest times the amount of money we had in there before. The whole point of compound interest is that you start earning interest on your interest, not just on the initial amount available. So every year when the bank goes to calculate your interest, it just looks at how much you had in the account, not where any of that money came from. So we get that the amount of money after 2 years is 1 plus r times the amount of money you had after 1 year. But we also know the amount of money you had after 1 year is p times 1 plus r. And so in fact we get that the amount of money you have after 2 years is p times 1 plus r squared. And this goes along with the interpretation of 1 plus r, which tells us how much we multiply our investment by each year. So in the first year, we went from p to p times 1 plus r. And then when we move from the first year to the second, we're going to multiply by 1 plus r again, because we're earning interest on our interest. And in fact, when we go to t3 of time 3, the amount we have after 3 years is going to be the amount we have after 2 years plus the rate, the interest rate, times the amount we had after 2 years, which is a2 times 1 plus r. But a2 is p times 1 plus r squared. And so we get p times 1 plus r cubed. So this tells us that when the number of times per year that you compound is just 1, then the formula that tells you how much money you have in your account looks like this. You'll take your principal times 1 plus your interest rate raised to the number of years that you've invested things. So then what happens if the number of times per year your interest is compounded is more than 1? So what if n is greater than 1? Now what this means is that n could be, say, 12, meaning that your interest is compounded monthly. And then every month your bank goes and looks at how much you have in your account and gives you some more. Well, now every month your account is now multiplied by not 1 plus r, but 1 plus r divided by n. The reason why it's r divided by n is that r, the interest rate, is always expressed as an annual interest rate. No matter whether you're looking at a credit card, a mortgage loan, a car loan, or a bank account, the interest rates that are given are always annual interest rates. But if the interest is being compounded every month, then you need to divide that interest rate by 12 in order to determine essentially your monthly interest rate. Or if your number of compoundings is daily, you would have to divide your interest rate by 365 to get your daily interest rate. So what this means, I wrote every month up here, I should say every period, where the number of periods per year is equal to n. So what this means is that after one period, the amount in your account is equal to your principal times 1 plus r divided by n. Then after 2 periods, the amount is equal to p times 1 plus r over n times 1 plus r over n, which is p times 1 plus r over n squared. So every time another period goes by, whether that's a month or a day, the amount in your account is multiplied by 1 plus r over n. And so after m periods, let's say the amount in your account is equal to p times 1 plus r over n raised to the mth. Now, usually it's more useful to us in practice to measure things in terms of years rather than periods. So we want to figure out, okay, well, how many periods are there in t years? So there are n periods per year, n compounding periods per year, and since that happens for t years, that means that m is equal to n times t. So if your interest is compounded monthly and you've had the account for 5 years, then that means that you've gone through 60 compounding periods, once per month for 5 years. So this gives us the formula for compound interest, and I'm going to write it down on the next page with a full definition, but this is how we come up with it. So the compound interest formula. The amount A of money in an account starting with a principal P for T years, compounded N times per year, with annual interest rate R, is the amount is equal to the principal times 1 plus the interest rate divided by the number of compounding periods per year raised to NT, the number of compounding periods per year times the number of years that the account has been active. So we can use this formula to answer many kinds of questions related to these kinds of problems. So, for example, if I invest $2,000 in an account paying 3% per year, compounded quarterly, how much will I have after 10 years? So for this, we need to identify what all the various pieces of the formula are. We're being asked to find how much you'll have after 10 years. So we're trying to find A. That means we need to identify P, R, N, and T. You'll always need to identify 4 of the quantities in this formula in order to determine the 5th one. So let's see, we are told that we start with $2,000, so we'll let P be 2,000. Paying 3% per year, that's the interest rate. Now, importantly, the interest rate always has to be expressed as a decimal, not a percent. So you need to convert your percentage into a decimal. 3% is 0.03. Compounded quarterly means that we're compounding 4 times per year, so N is 4. And then how much will I have after 10 years tells us that T in this case is 10. So let's plug all of those into our formula. We have A is equal to 2,000 times 1 plus 0.03 over 4 raised to the 4 times 10. And the nice thing is that using a scientific calculator like the Desmos one here, we can do all of this at once. And in fact, doing a whole expression like this at once is often less error prone than doing it in pieces. So let's go ahead and work this out. We've got 2,000 times 1 plus 0.03 divided by 4, and all that's going to be raised to 4 times, oops, I need parentheses there, raised to 4 times 10. So we can see from the calculator that this whole expression here gives us 2,696, and because this is in money, we want to round to 2 decimal places. We want to round to the nearest cent. So this tells us that after 10 years, investing money in this account, we will have $2,696.70. Now, some of you may be objecting here, saying, where are you finding a savings account paying 3% per year? You're probably not. However, this same formula also applies to things like investment accounts. If you have a mutual fund that pays you 3% per year, and if you take all the profits of it and invest it back into the mutual fund, the same formula applies. This same sort of formula applies in any sort of situation where the amount of stuff that you have, where having more stuff in the whatever it is and whatever you're measuring causes that thing to grow faster. And in particular, when the growth occurs on a discrete basis like this, like every month it goes jump, 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 rather than a continuous type of growth, then the compound interest formula here can be used. So it's not just applicable to dollars in savings accounts earning explicitly interest, but it can also be return on investment for lots of different kinds of situations. Okay, so that's how we do that. We can also very usefully use this formula to figure out how much we need to save in order to have a certain amount by a given date. So, for example, let's suppose that a father wants to invest money so that his newborn child will have $10,000 for a car in 18 years. If he can invest at 2.5% interest compounded daily, how much must he invest? All right, so in this case, we know how much the father wants to have at the end of the process, and we're trying to find how much he needs to invest now. So he knows that he wants to have $10,000 at the end of the whole process. We know that this is supposed to happen after 18 years, so that tells us that t is 18. We're told that he can invest at 2.5% interest, so converting that into a decimal, that's 0.025. And we're told it's compounded daily, so n in this case is 365. So if we plug all of that into the compound interest formula, what we get is 10,000 is equal to the principal times 1 plus 0.025 over 365 raised to 365 times 18. Now this allows us to solve for p. What we're going to do is we're going to divide both sides by this whole expression here. 365 times 18, 365 times 18, 1 plus 0.025 over 365, 1 plus 0.025 over 365. So we get that the principal he must invest is equal to 10,000 divided by 1 plus 0.025 over 365 raised to the 365 times 18. And this is again something we can do all at once in the calculator. So we've got the expression we want to figure out is 10,000 divided by 1 plus 0.025 divided by 365 raised to the 365 times, oh, I did it again, in parentheses, 365 times 18, and we get 6,376 and 38. So in order to get the $10,000 at the end of 18 years, given these investment possibilities, the father must invest $6,376.38 now, and he will have $10,000 at the end of 18 years. So this is one of the most important uses of exponential functions. Now, one thing that you will find if you run a few examples is that the more often you compound your interest, the more money you have at the end. Compounding daily gives you more money than compounding quarterly, which gives you more money than compounding annually. And so by increasing the number of compoundings a year that you do, you get more and more money. So the question is, well, what's the limit here? Could I get myself a huge amount of money simply by compounding a ridiculous amount of time, say every second or every nanosecond? And the answer is, unfortunately, no. There is a limit, but determining what this limit is leads us to one of the most important numbers in all of mathematics. So the question is, what happens if we increase the number of compoundings as far as possible? So every minute, every second, every nanosecond, so forth and so on. Well, there's a more detailed proof of what's going on in the textbook. I want to look at a slightly simplified example here so that we can get an idea of what's going on. Let's simplify, or it's a simple example. Let's let the principal be 1. Let's imagine we're investing a single dollar, and we're seeing how big that single dollar can get. And we're just going to invest for 1 year. We're going to invest a single dollar for a single year, see how big it can get. First of all, we're going to, or third of all, we're going to do it at an interest rate of 100%. So if this were compounded annually, then at the end of a year, I'd get 100% interest and get another dollar. So if we were compounding annually, we would get $2. So compounding more often will get me, well, certainly more than $2. And we will let n be, well, large, and see what we get. So if we do this, then our amount will be 1 raised to the 1 plus 1 for the rate over n raised to the n times t, which is 1. So that's just 1 plus 1 over n raised to the n. And we can start to see, if we look at this, why this question arises. As n gets big, as n goes towards infinity, this 1 plus 1 over n expression actually goes to 1. And that's because the 1 over n piece is going to go to 0. The graph of 1 over n has a horizontal asymptote at 0. When n is huge, 1 over n is tiny. And so when n is very, very large, 1 plus 1 over n is very close to just 1. And 1 raised to anything is just 1. And so what that says to us is that the base of this exponential expression here is trying to force the whole expression to be small. On the other hand, as as n goes towards infinity, this exponent here goes off towards infinity and is getting huge. And if we take a number bigger than 1 and we raise it to a large number, we're going to get a very large number because we're multiplying a whole bunch of things that are all bigger than 1 together. That's going to give us a large number. And so we've got these two pieces of the puzzle that are sort of fighting against one another. It's actually very similar to when we were talking about the end behavior of rational functions and looking at the degrees of the numerator and denominator and asking which one wins, which one's stronger. We've got the same situation here. The base of this expression is trying to make everything small. The exponent on this expression is trying to make everything big. Which one wins? Let's do some experiments to see what we can get. So, and by experiments, of course, I just mean computation. Computations are the experiments of mathematics. So let's take some large values of n and see what we get when we plug into 1 plus 1 over n to the n. In other words, how much money will I have in my account after 1 year under these scenarios for various amounts of compoundings. So let's start simple. We can compound once a year, 10 times a year, 100 times a year, 1,000 times a year, and then I want to go really big. I want to do 1,000,000 times per year. And let's see what happens to these numbers. Once again, I'm going to pull out my calculator because, of course, doing this by hand would be terribly tedious. So in the first case, if n is 1, then we have 1 plus 1 over 1 raised to the first power, which is 2. And we actually already said that. We already mentioned that if we were compounding annually, then we would just wait until the end of the year, get our 100% interest, and get $1 extra. But what if we compounded 10 times a year? If we compounded 10 times a year, then we get quite a lot more. We get 2.59, and I'm going to go ahead and get us some more decimal places here. We have 2.5937, so already we've made quite a lot more than we did before. Now, what if we compound not 10 times a year, but 100 times a year? Well, it keeps going up, 2.7048. But you'll notice that it didn't go up quite as much as it did before. And so what if we compound 1,000 times per year? So this is about 3 times a day. 2.7169. And you can see that the money train has slowed a little bit. When we went from 1 to 10, we got a lot more money for our investment. But moving from 100 to 1,000 gets us a little over 1 cent more. So let's go ahead and say, well, what if we go ahead and do it 1,000,000 times a year? And from there we get 2.7182, etc. And you can see that we've barely increased at all. So the point is that as n gets huge, as our number of compoundings per year gets enormous, we don't actually get unlimited amounts of money. There's a limit to how much you can earn from simply from compounding more often. And in fact, this number that we get, or the number that we're approaching here, has a special name. It turns out to be vitally important in many areas of mathematics. So the number that 1 plus 1 over n to the n gets close to as n goes to infinity is called Euler's number and is denoted with simply a lowercase e. Euler was a German mathematician in the 18th century who was incredibly prolific. And he contends for the title of greatest mathematician of all time. One of the things that he did is he studied these types of relationships, these types of exponential relationships. He was not the first to note the existence of this special number, but he was the first to really take advantage of it, and that's why his name gets attached to it. Now, e is not a variable, it is a specific number, but like pi, it refers to a number that is irrational, which means that the only way we have of describing it is by giving it a symbol. E is equal to 2.71828, etc., etc. You can memorize digits of e like people memorize digits of pi. For practical use, we don't typically need too many of them, but a calculator can give you a whole bunch. Now, let's see. Most calculators have a button which will give you the number e, and so here we do, for instance, in the Desmos, we've got the number e here, and you'll notice that if I look at the number e, it's actually very, very close to what we had before, 2.71828. They only differ in the 6th decimal place, and if we were to plug in values of n for, say, a billion or a trillion, we would get even closer to the correct value of e. So e is one of the most important numbers in all of mathematics. It is as important as pi even, but not quite as accessible in say, elementary school. So most people see e much later than they see pi, but mathematically it's even more important. Now, as it turns out, we can express what happens in this in the compound interest scenario as n gets very, very large, involving e even outside this very simple scenario like we've got here. So, a fact which unfortunately we're not going to have time to prove is the following. As n goes to infinity, as the number of compoundings per year grow and grow and grow, the expression p1 plus r over n to the nt, which we had before as the amount of the in the account with the various compoundings here, this expression goes to pe raised to the rt. So as n gets bigger and bigger and bigger, then this whole expression here gets closer and closer to this expression over here. And you can find a computation that that handles some of this in the textbook. Now, what this means is that we can define a new kind of compounding, which is referred to as continuous compounding. And in continuous compounding, you're not compounding every day or even every hour or every second, every millisecond. You are compounding literally every instant on the interest that was earned on all previous instants. It's not a matter of just doing the compoundings really, really fast. It's continuous. It's constant compounding. This kind of constant growth is actually more commonly used in disciplines like biology, when you're trying to model the growth of, say, a bacterium in a lab, or when talking about an economy, which doesn't just go up in spurts like this, but is constantly changing, constantly growing or shrinking. So we can define it this way. The amount of money in an account with principal P, interest rate R, and compounded continuously is the amount is equal to P e to the RT. This is the formula that most people talk about when they talk about exponential growth. So people might say that the economy grows exponentially at a rate of 2%, something like this. That means that they're referring to an equation of this type, where the size of the economy, however you're measuring that, is equal to some size of the economy at a previous time times e raised to a rate times the time between the two moments that you're measuring it. So let's do a couple of examples with this. Let's say that I have invested $700 in an account paying I've invested $700 in an account paying 12% compounded continuously. How much will I have after 6 years? So the key that tells you that you're using the continuous compounding formula rather than the compound interest formula is this word continuously. Whenever you're dealing with a problem that involves interest, you need to have some sort of information about how often it's compounded. Now, if you're given absolutely no information at all, the default is annual compounding, but that's very rare. You should almost always have some sort of information that tells you how often you're compounding, or you will have the phrase continuous compounding, which means that we're going to use the formula A is equal to P e to the RT. Now we need to identify 3 of the quantities here, and in this case, P is 700, R is 0.12, and T is 6. So that means that the amount I have in my account will be equal to 700 times e to the 0.12 times 6. And this is something that we can do in the calculator. And we can say that the amount is 700 times e raised to the 0.12 times 6. And we see that that'll get $1,438.10. We can also go the other way. Let's do another example. A colony. Let me get this out of the way for a second. A colony of bacteria grow at a rate, at a continuous rate of 50% per hour. If there were 3 million bacteria, there were 3 million bacteria 12 hours after the experiment started, how many were there originally? All right, so this is another example of exponential growth. In this case, we're told that we're given a continuous rate, so we know that we're going to use the formula A equals P e to the RT. And we need to identify some of the other ones in here. Now, in this case, because we're not dealing with financial situations, the rates are not always given per year. What you need to make sure of is that the rate that you're given is being measured using the same units as the time that you use. In this case, they are. We're told that our rate is at 50% per hour, and we're told that the time involved is going to be 12 hours. So those match up. Our next example, we'll see one where they don't, and so you can see what sort of conversions you have to do. So in this case, we have that the growth rate is 50%, which we write as 0.5. Now we're told that there's 3 million bacteria 12 hours after the experiment started. So that means that the A value here, the amount at the end, is 3 million. Now, I'm also going to do a little trick here which makes things easier. When we're dealing with very, very large quantities, typically you don't want to include the whole number, 3 million like this. What you'll do is you'll say, in this problem, I'm measuring my population in terms of millions of bacteria. So how many millions of bacteria were there at the end of the problem? Well, there were 3 millions of bacteria. And then when we calculate our P at the end of the problem, it will also be measured in millions of bacteria. And then finally, the time of this problem is 12. There were 12 hours between the start and the end of this problem. So let's go ahead and use these. So that tells us that 3 is equal to P, the initial amount, which we don't know, times E raised to the 0.5 times 12. And therefore, that means that P is equal to 3 divided by e to the 0.5 times 12. Just solving for P by dividing the exponential expression on both sides. Now this we can do in the calculator. And so we have that P is equal to 3 divided by e raised to the 0.5 times 12. And what we get is that there were 0.00743, or 44, let me round it. Okay, so now in our answer, we should try to give an answer in the same sort of form that the question was asked. The question was asked in terms of millions of bacteria, so our answer should spell out there were now 0.00744 million is not really that useful, so what we can do, getting 0.00744 million is equal to 7.44 thousand by moving the decimal place over three places, or just 7,440. So there were approximately 7,440 bacteria when the experiment started. Now, problems like this will always indicate how many decimal places to round to or where to round things to. I am probably rounding much too narrowly here. The 3 million bacteria is probably not very precise. It would probably be anywhere between 2.9 and 3.1, something like this. So I should probably have just said something like there are approximately 7,400 bacteria, or maybe even approximately 7,000 bacteria. If you are using these techniques in a professional capacity, each professional will have their own rules for how to handle precision like this and how much to round appropriately. So pay attention to those rules when you go on to apply this. All right, lastly, we have the following. The exponential formulas that we have can be used to describe exponential decay as well as exponential growth. In exponential decay, the amount of reduction in a quantity that happens is proportional to the size of it. So the more of something there is, the faster it decreases, but then as there's less of it, the rate of decay slows. So exponential decay happens when our growth rate, or our interest rate, or growth rate, R is negative. So let's see an example of how we use that. A certain radioactive isotope decays continuously at a rate of 8% per minute. A very unstable radioactive isotope, actually only about medium stable. Many decay very, very quickly, but this one decays at a rate of 8% per minute. How much will be left after 2 hours if we start with 10 kilograms of the material? So in this case, we can still use the familiar continuous growth or decay formula, A equals PE to the RT. Now, there are a few things that we need to determine. Some of them are easy. Our initial amount is going to be 10, and that's being measured in kilograms. So our amount at the end is going to be measured in kilograms also. Now, our rate R is going to be 0.08, and that's per minute. Our time is given as 2 hours. That's the amount of time between the beginning and the end of the experiment. But we can't use t equals 2 because the units of that, hours, don't match up with the units of the rate. Now, when you have this situation, when you have the rate is being measured by in one unit and the amount of time is being measured in another unit, you should always change your time to match the units of the rate. So rather than saying 2 hours, we're going to convert that to minutes. 2 hours is 120, and that's being measured in minutes. Now everything is consistent with one another and the formula will work. So that tells us that the amount of material we'll have will be 10 times e to the 0.08. Oh, sorry, I backed up, I forgot. It's very important here. The rate's actually negative 0.08 because this is decay. The amount of radioactive material that we have is decreasing because those elements are changing into other elements through radioactive decay. And so the rate R here is negative. A negative rate corresponds to exponential decay. So R is negative 0.08. The time is 120 minutes. And so we can calculate the amount of radioactive material we have left. This will be 10 times e raised to the negative 0.08 times 120. and that will give us 6.77, I'll leave it there, 6.77 times 10 to the negative 4th kilograms. So converting that we can convert that into non-scientific notation by moving the decimal place 4 units to the left. That's 0.000677 kilograms. So a very, very small amount left. So even though it only decreases at a rate of 8% per minute, when you decrease by 8% per minute for 120 minutes, then almost everything is gone. We started with 10 kilograms, wind up with less than less than 0.1% of a kilogram at the end. So this is how we can use the same formulas for exponential growth in order to get exponential decay. And these types of growths and decay happen all over the real world, all over applications, both scientific and industrial.